Physics Chapter 1 Electrostatic. The first subtopic is Coulomb's law. Coulomb's law states that the force between 2 point charges which are separated by a distance is directly proportional to the product of the charges and inversely proportional to the square of distance between them. So in short, the formula is force is equal to k(q) over r squared, where k can be written as 1 over 4 pi epsilon naught. The constant of proportionality K is equals to 9 times 10 to the power of 9 Newton meter square per coulomb square. There are two kinds of charges, positive charge and negative charge. Like charge will repel each other and unlike charge will attract each other. From here we see that plus Q charge and plus Q charge will repel each other with the force directed away from each other. And here plus Q charge and negative Q charge will have the force directed towards each other. This is the graph of F against R and F against 1 over R squared. If we take a look at the Coulomb's law and Newton's law of gravitation, we can spot some similarity between these two laws equation. First, F equals to k(q) over R squared and F equals to gmm over R squared. The difference is just that in Coulomb's law, the force is the electric force, while in the Newton's law, the force is gravitational force. And in Coulomb's law, it is between 2 point charges, while in Newton's law, it's between 2 point masses in the universe. Another difference is, in Coulomb's law, the force can be either attractive or repulsive, while in Newton's law of gravitation, the gravitational force can only be attractive towards each other. In Coulomb's law, the electric force is very short range, but in the Newton's law of gravitation, the force can be very long range. Example for Coulomb's law. 3 point charges of positive 2 microcoulomb, negative 3 microcoulomb, and plus 4 microcoulomb are fixed at their respective position as shown in the figure. Calculate the force on the charge of negative 3 microcoulomb by the other two charges. To solve this question, we need to label the force first. First, we label the force F1 and F2. Since the negative charge is attracted to the positive charge, the force is directed towards the positive charge. And then we label the resultant force in between these two forces. And then we label the angle. The solution, we need to calculate the F1 first. By using the formula F1 equals to Q1 over R1 squared, we can get the magnitude of F1 is equals to 6 times 10 to the power of negative 3 Newton, while the magnitude of F2 is equals to 6.8 times 10 to the power of negative 3 Newton. To find the resultant force, we need to make use of the Pythagoras theorem by squaring both and adding up together and square root the sum together. We can get the resultant force is 9.1 times 10 to the power of negative 3 Newton. And the angle can be used by the trigonometry method. Tangent theta equals to F1, which is the y component, after F2, which is the x component. And then we can get the theta is equals to 41.4 degrees. To the next subtopic, electric field. An electric field is the region where a force acts on a charged body. An electric field is represented by lines of forces, which are actually the path of a free positive charge in a field. The direction of electric field is taken as the direction of the force on the free positive charge. Take this diagram as example. If we place a positive charge here, the positive charge will repel the positive charge, therefore the force will be directed outwards of the positive charge. Therefore, the electric field's line is directed outwards of the positive charge. For this diagram, if we place a positive charge here, the positive charge will be attracted towards the negative charge. Therefore, the electric field is directed in this direction. So the electric field's line is directed towards the negative charge. The electric field strength. The electric field strength at a point in an electric field is the force per unit positive test charge at that point. The formula is E is equals to F over Q naught. The unit is Newton per Coulomb or Volt per meter. By using Coulomb's law, we substitute in the F is equals to Q naught over R squared. By substitute in this formula, therefore another formula for E is equals to KQ over R squared. The direction of E is always away from the positive Q, while the electric field strength E at a distance R from a point charge which is negative. Take note this is negative and this is positive. For negative, the E is equals to negative Q over R squared. Electric field due to 2-point charges. Take a look at this diagram. The point P is located between two charges. One is the negative charge, another is the positive charge. It experiences two electric fields combined by the two charges. The electric field E at point P is the resultant of the electric field E plus due to the positive charge, and the resultant of E negative due to the negative charge. So in order to calculate the resultant E, we need to sum out the E plus and the E negative together. In order to visualize more clearly, we can label the direction of electric field E plus directed away from the positive charge, and then the E negative directed towards the negative charge. Therefore, the resultant electric field will be between these two electric fields. Example for electric field strength. Find the magnitude and direction of electric field strength at point P. First, same as the Coulomb's law, we need to label the direction of electric field first. First, we label the x and y axis, and then we label the electric field direction with E1 pointed away from positive charge and E2 pointed towards the negative charge. And then, since the E2 magnitude is greater, the resultant E will be somewhere below the x-axis, and then we label the angle theta. In order to find the resultant E, we need to calculate the magnitude of E1 and E2 first. We calculate the E1 by using the formula KQ over R, and then we get 1.8 times 10 to the power of 6, same as E2, and we get 7.2 times 10 to the power of 6. And then these two electric field is not in the x and y, is not directly in the x and y axis. Therefore, we need to resolve them into x and y components by forming this table. The x component of E1 is E1 cos theta, where the theta is 45 degree. And the y component for E1 is E1 sin theta. For E2, x component is E2 cos theta. For y component, since the y component of E2 is pointed downwards, so we need to add on the negative sign. Therefore, it is negative E2 sin theta. And then we sum out together the x component and the y component. To find the resultant electric field, we need to take the Pythagoras theorem by squaring x component and squaring y component and adding up together, and then square root them together. And then we get 7.42 times 10 to the power of 6. For the angle, we take the trigonometry function tan tangent theta is equals to EY, which is the y component, over the x component. And then we get the theta will be negative 30.99, which is below the positive x-axis.
Hello everyone. Now I'm going to discuss about chapter 1.3, electric potential. Introduction. The electric potential V at a point in an electric potential V at a point in an electric field is the work done to bring a unit charge from infinity to the point. As you all know, V equals to W over Q. E is a scalar quantity, which means it has no direction. The SI units is B or J over C. First of all, electric potential energy. W is equals to KQQ multiply 1 over R A minus 1 over R B. Since we know that electric potential energy is an energy bringing the charge from infinity to a direction, so we can assume that the RB equals to infinity. So we can cancel it and we can get W equals to KQQ over R. Work done equals to U. Hence, we can assume that U equals to KQQ over R. U equals to electric potential energy at a point. At the same time, V equals to KQ over R. So, we can simplify the formula U become U equals to Q multiply KQ over R. We substitute V into the solution, we can get U equals to QV. Here are two situations for equipotential surface. The first one is the point charge. The second one is the uniform electric field. Note that no work is done in moving a charge from one point to an equipotential surface to another point on the same surface. W equals to 0. If there is 2 point charges at the same line at the point charge, the electric field produced by a point charge, no extra work is needed to move them around the point charge, around the circle. Similarly, if there is 2 point charges at the same line at the uniform electric field, no extra work is needed. Next, electric potential difference. Delta V equals to V final minus V initial, which equals to VA minus VB. There are two formulas for V. V equals to W over Q, and also V equals to KQ over R. So, electric potential needed to move a charge from B to A. So, since the direction from a point charge to the A is shorter than the Q, the charge from the B, which R2. So, the shorter the R, the larger the V. So, we use VA minus VB. At the same time, we can also say that delta V equals to WA minus WB over Q. Next, change in electric potential energy, delta U. Delta U equals to UAB, which means UA minus UB. Since we all know that U equals to QV, and we can assume that QVA minus QVB. We move up the Q, let it be Q multiply VA minus VB. So, VA minus VB equals to delta V. Hence, delta U equals to Q multiply delta V. So, the summary of this subtopic 1.3 electric potential is that we have 4 formulas right here that you have to remember the time which you have to use it in your calculation. First of all is electric potential is equals to V equals W over Q. Is also equals to KQ over R. Electric potential energy is U equals to Q multiply KQ over R, which means QV. Next
To
one,
find electric potential energy for a
difference.
system,
Delta
as for
V
the two charges,
equals
we have to use
V
U equals to K to the
final
product of
minus
Q1
V
and
initial.
Q2 over the distance
Lastly,
between
the
Q1 and
change in
Q2. As for
electric
the three
potential
charges,
energy,
we have to use U equals
delta
to
U
K to the bracket of
equals to
product of Q1
UA
and
minus
Q2
UB
over the
and
distance
equals
between
to
Q1 and Q2
QVA minus
plus the
QVB.
product of Q1 and
We
Q3
simplify
over
it
the
and
distance
we'll
between
get
Q1 and Q3
Q
plus the product of
multiply
Q2
delta
and
V.
Q3 over the distance between Q2 and
That's all
Q3.
from me. Thank
Charge
you.
in a uniform field. The electric field lines will move from positive to negative. Therefore, proton will be attracted to the negative plate while the electron will be attracted to the positive plate. As you can see from the diagram, the proton is moving upwards while the electron is moving downwards. When electron or proton is moving in a parabolic trajectory, we can use the concept of projectile motion